So this is the next chapter I am starting right now, that is the pollution. And in the pollution, we will start with the noise pollution. Then we will go further to the air and water pollution. Then this particular unit would be also completed. This is the sixth unit in the syllabus. 5 units we have already completed till the energy and environment. The geoscience we have completed, and the starting 3 units we have also completed. Now we are going to the sixth unit. Half of the syllabus already completed. So now this is the environmental pollution, and in the environmental pollution we have to start with the noise pollution. So let's see. So very basic thing we have to start with, that is what is the noise. So what is the noise? Noise is any kind of sound, especially one that is unpleasant, that is very loud, and that can damage the any organism's ear or any organism's hearing organs. So that can be termed as a noise. So now what is the sound wave? Before understanding the noise, we have to understand what is the sound. So sound is basically a kind of wave. And what kind of wave? Wave which is having a kind of fixed wavelength, a kind of amplitude, a kind of height that we have already seen in the previous lectures as well. So that parts of the waves are creating a kind of sound or kind of volume, you can say. So let's see the different parts of wave here. So this is the wave, and here you can see this is going up and down motion. So this portion is called as crest, which is going upside, and this portion is called as trough, which is going downside. So here in this particular crest section, here you can see this is starting from crest and up to this crest. This particular portion is called as wavelength, which is denoted in lambda. Then the height, it means crest to trough depth, or you can say trough to crest height. This portion is called as the wave height h. Wave height h, half of the wave height h is called as amplitude, which is termed as A. So we can say that the h or wave height is actually 2 way, which is 2 multiplied by the amplitude. And this is the mean level. So this is what a particular wave is. So this noise or wave or sound is measured in terms of decibel value or in terms of hertz value. So there is a fixed range of audible frequency of the human ears, that is in the range of 20 to 20,000 hertz or 0 to 120 decibel. So only in this range the human can hear sound. If the sound is more than this 20,000 hertz or 120 decibels, so that can damage the human ear. If it is less than 0 decimal or less than the 20 hertz, so the human ears are not that much evolved, you can say, or not that much developed, so they can hear the sound less than the 20 hertz or 0 decibel. So this is the human audible frequency that you have to remember. So this is all about the noise and the sound waves. So before going further in this particular chapter, we have to understand some basic formula here. So the very basic formula, velocity of any particular wave is how much? That is equals to the frequency of wave, that is this mu, and that is multiplied by the wavelength of that wave. So if you multiply the both, you will get the velocity of that particular wave. Then we have the relationship of the time period or the oscillation period and frequency. So frequency is equals to 1 divided by the oscillation period or t. And similarly, t equals to 1 divided by mu or frequency. So here, if I replace this mu with the help of 1 by t, so the velocity of the wave can be calculated as lambda divided by t. So lambda is the wavelength here and divided by the oscillation period. So in per unit time, how many times it is oscillating? It is going from the wave crest to crest or wave trough to trough. That is that oscillation period is. So that is how you can calculate the velocity of any wave. Now, velocity of any wave can be calculated with the help of this formula as well. So velocity of any wave, v is equals to 344 under root t divided by t naught. Here T naught and T are temperature. So T naught is the reference temperature, or you can say room temperature, and T is the that temperature in which the question is asking. So here the T value you have to provide it in Kelvin, because Kelvin is the SI unit of temperature. So if it is in the degree Celsius, Add 273 to that. Suppose room temperature is 20 degrees Celsius. So this would be added by 273. So 273 plus 20, 293 Kelvin. So this is what the basic formulas, and based on these formulas there is a question asked in the examination. Try to solve it. This is the question. How thick a sound barrier to be made if it is to attenuate efficiently sound transmitted at 5 kilohertz? So options are 2 centimeter, 3.3 centimeter, 6.6 centimeter, and 2 millimeter. So try to solve it. The frequency is provided to you here in this particular question, that is the 5 kilohertz. It is asking about the sound barrier. Sound barrier means that much amount of thickness of a wall or maybe sound barrier I want to made, which can attenuate sufficiently the 5 kilohertz wavelength of the sound. So what you have to do here, you have to just calculate the lambda, and that lambda value would be your answer. Why? Because that lambda value or wavelength, suppose you have calculated and you have created more than the wavelength of that sound wave. So that particular sound can be effectively attenuated. Attenuated means stopped. So you don't want the sound should go out of this particular wall. So if suppose sound is coming like this, so automatically the sound will stop here and nothing will come out in this particular side. So that is attenuated. So suppose if you have that much thickness of a wall, which is more than the lambda value, the wavelength value. So this is more than the lambda value. So then the sound can be attenuated effectively. So calculate the lambda, that would be your answer. So let's see the solution. So we all know velocity we can calculate with the help of 344 T divided by T naught meter per second. So I will use this formula. So temperature is not provided in the question. So we will assume that the temperature is in the room temperature, or that is the 20 degrees Celsius. So here T and T naught both are equal. So both would be cancelled. And our velocity we will get as 344 meter per second. So in air, 344 meter per second of the attenuation we are getting. So now we will use this particular formula, that is velocity equals to mu multiplied by lambda, or frequency multiplied by the wavelength. So I have to calculate the wavelength, that is the lambda. So lambda is equals to V divided by mu here. V is the velocity, mu is the frequency of the wavelength, that is given as 5 kilohertz. And we have calculated the velocity 344. So for the ease of calculation, just take this 344 as 350 and 5 kilohertz, so that is 5000 hertz. So 5000 you have to divide. So this is this cancelled, and this is 35 divided by 500. This would be 7. This would be 100. This is 0.07 meter, or I can say 7 centimeter. 7 centimeter of the wall can easily attenuate this much amount of wavelength of the sound wave. That is the meaning of this particular solution. So I hope this is clear to you. Let's see these options here. Nearest option here is the 6.6 centimeter, which is the right answer. So I hope this is clear to you. One thing, remember that the velocity formula I have provided to you, this is only true in the case of air. If suppose in the question it is saying that sound is moving on the water, then this formula cannot be worked. In the water, the velocity of sound will change. And how much changed? Changed by a big amount. This would be 1480. So in water, you have to replace this 344 with 1480, and that's all you have to do. The remaining all thing would be same. So suppose if in the question it is saying that how much of the sound barrier I have to made in the water to just stop this particular sound, attenuate that particular sound which is moving on the water. Then in the formula, in the place of 344, you have to use 1480. So that's all about this particular solution. So I hope this is clear to you.